Hello and welcome to this video in physics. So in this video we are going to be looking into momentum physics. We will critically look into momentum and we are going to be defining the meaning of momentum, and then we'll look into impulse as it concerns momentum. We'll also look into Newton's laws of motion as they also concern momentum. Particularly we are going to be paying attention to the second and third laws of motion. And in each stage, we are going to be backing up all our explanation with a solved example. So sit tight while we begin the class. Now, what is momentum? Momentum can simply be defined in simple terms as a product of mass of a body and the velocity of the body. So for instance, let's say I have an object like a ball of mass m meant to move in this direction. Okay, with a speed v. Now momentum is symbolized by the letter p, and this is simply equal to the product of the mass and the velocity. Now we all know that the unit of mass is kilograms and unit of velocity is the meters per second. So this simply means that the unit of momentum is kilograms meters per second. Now let's say I have an object which has a mass of 5 kg and the object is moving with a speed v equals 3 meters per second. What becomes momentum in this case? Okay, momentum is simply going to be what? Mass times speed or velocity, so which is 5 times 3, and that simply gives us 15 kilograms meters per second. Okay, so in simple terms, momentum can simply be defined as a product of mass and velocity. Now it's important for you to know that since an object must have a velocity, it means that that object must have a specific direction to which it is moving. So that simply means that momentum is what? A vector quantity, because the object will always move in the direction of the velocity. Since there is velocity, then it means momentum is a vector quantity. Now, having talked about momentum, there is another quantity that is of paramount importance in the discussion of momentum, and that quantity is known as impulse. Okay, that quantity is known as impulse. Now impulse is another term that must be defined in the subject of momentum. Now what is impulse? Impulse simply means a large amount of force which acts within a very short interval of time. A large varying amount of force which acts within a very short interval of time. Let's take for instance, you hit your head against a wall or you slap your friend. Now you are exerting a varying amount of force, a large amount of force within a very short interval of time. That impact, that effect is called an impulse. It can also be called an impact. For instance, if you play a ball against a wall, there is collision between the ball and the wall at a very short interval of time. That large amount of force, that impact, is what is called impulse. And mathematically, impulse can simply be defined. Okay, so impulse is symbolized by capital letter I. So impulse is symbolized by capital letter I, and mathematically it is simply the product of force times the time which that action takes place. And you know that the unit of force is the newtons, right? The unit of force is the newtons and the unit of time is the seconds. That means impulse is measured in newtons seconds. Now let's say we have a force. Let's say a boy exerts a force of 50 newtons, F equals 50 newtons on an object within a time frame of 10 seconds. within a time frame of 10 seconds. That means the impulse or the impact felt on that object I is simply equal to what? 50 times 10, and that will simply give us 500 Newton seconds. So the product of force and the time to which that action takes place gives us what is called the impulse, which can otherwise be called impact felt. All right, now we've talked about momentum and we've explained impulse. How then does impulse connect with momentum? We're going to find out that in the next thing we're going to be discussing, which is the Newton's laws of motion as they concern momentum. And as I said earlier, we're going to be paying attention to the second law of motion and third law of motion. We're not going to be discussing the first law, right? So let's take a look at Newton's second law of motion and how it affects momentum. Okay. Now, the Newton's second law of motion states that the rate of change of linear momentum is proportional to the impressed force and takes place in the direction of that force. Okay, now mathematically, this simply means that the rate of change of linear momentum, which means if I have, remember momentum simply means mass times velocity. So change in momentum means we have initial momentum and we have final momentum. So let's say we have mv minus mu all over t. Okay, when you divide by t, you talk about rate, right? So rate there simply means time, and this is directly proportional to what? The force, and it must be in the direction of that force. The rate of change of linear momentum is directly proportional to an impressed force, and it must be in the direction of the force. This is simply the Newton's second law of motion. All right, now seeing that mass is constant, we can simply factor out mass, or you can also write this simply by saying force is also directly proportional to the rate of change of linear momentum, mv minus mu all over the time. Now keeping in mind that v and u symbolizes what? The final and initial velocity. So if we are going to be factoring mass, so this simply implies force is directly proportional to mass is common into v minus u all over t. And you know that v minus u over t simply stands for what? Acceleration. Okay, so recall that acceleration is simply the change in velocity with respect to time. So this simply implies that our force is now directly proportional towards mass times acceleration. Now, if I remove the proportionality sign, I'm going to introduce a constant, which simply implies that force is actually what? Km times A, where this constant is dimensionless and is taken as what? 1. So if constant k is taken as 1, this simply implies that our force now is equal to mass times acceleration, which is the Newton's second law of motion. But how did this law come about? The rate of change of linear momentum is directly proportional towards force. Now let's fall back to this aspect of the law. Rate of change of linear momentum directly proportional to force. Let's fall back to this aspect of the law. Okay. So we said that force is directly proportional to mv minus mu all over t, which is the rate of change of linear momentum. Now let's cross multiply both sides, or let's multiply both sides with what? Time. This simply implies that force times time is now going to be what? Okay, let's use our direct proportionality. Is now going to be directly proportional, okay, to mv minus mu. Now once again, let's introduce our constant to remove this proportionality sign. So this simply implies that force times time is going to be equal to K being the constant multiplying by mv minus mu. Now, where K is dimensionless and you take K simply as 1, if that is the case, then you're going to have that force times time is equal to mv minus mu. Now, what does mv means? Final momentum, and mu initial momentum. But on the left hand side, we have something interesting: force times time. And you remember we said earlier, recall, we said that impulse is a product of force and time. So you see that the rate of change, so you see that the change of momentum or change in momentum simply gives us what? Impulse. So which means impulse is another way of what? Expressing momentum. The change of momentum is equivalent to impulse. So this is how impulse concerns momentum, and this can be found from the use of the second law of motion. Now let's pick a little example to explain this aspect of the law to momentum. All right, so let's consider this question to explain the concept of Newton's second law of motion as it pertains to momentum. The question says a ball of mass 0.4 kg moving at a velocity of 25 meters per second is suddenly hit by a force of 7 newtons for a time of 0.05 seconds. Find the final velocity of motion. Now let's pick out our parameters, please. We were given a ball of mass, so mass m was given as 0.4 kg. Okay, 0.4 kg, moving at a velocity of 25 meters per second. So we'll have our velocity v equals 25 meters per second. Now it is being hit by a force of 7 newtons. So we have a force there, F equals 7 newtons. Okay, for a time of 0.05 seconds, and we're given time t to be equal to 0.05 seconds. Now the question is asking us to find the final velocity of motion, v. Okay, so let's change this v here. Let's change this v to be u, right, to indicate initial speed. Let's change it to be u. So u is given simply as 25 meters per second. That's the initial velocity. Okay, now we learned from Newton's second law of motion that the product of force and time, which is impulse, is equal to the change in momentum, which is mv minus mu. And if you take a look at this carefully, you see that mass is constant, so you can easily factor out mass, which is m into v minus u, right? Okay, so what then is force? Force was given in the equation as 7. So you have 7 times, the time there is 0.05 seconds. So 7 times 0.05 is going to be equal to m, and the mass was given there as 0.4 kg. So you have 0.4 multiplied through by v minus u. V being the final speed is what we are looking for, minus u being the initial speed was given as 25 meters per second. So with this, the solution is self-explanatory. Let's obtain 7 multiplies 0.05. That simply gives us 0.35. So we have 0.35. Sorry. So we have 0.35 to be equal to 0.4 into v minus 25. So let's make this easier on us. Simply divide both sides by 0.4. So I'll simply have 0.35 divides 0.4, and this will be equal to v minus 25, right? So this simply implies, let's obtain 0.35 divided 0.4. This simply gives us 0.875. So we have 0.875 875, and that is equal to v minus 25. Okay, so with this we can easily make v subject. Simply send minus 25 over to this side of the equation. We are now going to have that 0.875 plus 25 is going to be equal to v. Remember when you send a negative sign over an equal to sign, it becomes positive, right? So this simply implies that our final velocity v is going to be equal to, that is 25 25.875 meters per second. So for that given object, this becomes the final speed when it is being hit by that force. All right, so this explains the concept of Newton's second law of motion as it contains or as it concerns momentum. And it also goes as far as letting you know that momentum, or the change in momentum, is equal to impulse. Now let's consider the third law of motion and how it affects momentum. Now let's take a look at Newton's third law of motion as it concerns momentum. The third law of motion simply states that action and reaction are equal and opposite. Now this law simply brings about the law of conservation of linear momentum. Action and reaction are equal and opposite. What then is a law of conservation of linear momentum? The law simply states that if two or more bodies collide in a closed system, the total momentum after the collision is equal to the total momentum before the collision. So when two or more bodies collide in a closed system, now when they say a closed system, it simply means a system where an external force cannot act. It is simply isolated from the environment. There's no external effect or air effect, anything external, atmospheric effect on it cannot take place. So it means isolated or closed system. So let's say we have a ball of mass. Let's say we have two balls of mass. This is ball A, okay, and it has a mass. Call that mass MA. Now this ball moves in this direction. Now I have another ball of mass. This ball is ball B, and it has a mass. Called this mass MB, moving in the opposite direction. Okay, let the speed of ball A be labeled as UA and the speed of ball B be labeled as UB. This is now before collision. So this is a situation where you have two balls moving opposite one another. So you simply call this is before collision. Okay, this is before collision. All right, now during collision you simply have something like this where the two objects simply collide with one another. So you have ball A and you have ball B. This is what? At collision. This is at collision. Now after collision, what happens is the mass of the object play a very key role after collision. If the mass of object A is larger than that of object B, it means that the objects or the two objects after collision will move in the same direction as object A, and vice versa. So it means that speed doesn't really play a role here. Ball B can have a higher speed than ball A. If ball A has a higher mass than ball B, after collision the two objects will move in the same direction as ball A if ball A has a higher mass. So let's take for instance that ball A has a higher mass. So after collision, what happens is you have the two objects moving towards the direction of ball A. Okay, So after collision, you have the two objects moving towards the direction of ball A. So this is ball A, okay, and you have ball B moving in the same direction as A. Now the speed in this case, we call that the final speed, VB. This is VA, and this is VB, which is final speed of ball A and ball B. Their masses remains the same, MA and MB. Of course, masses remains the same. Okay, so this is afterwards collision. Okay, this is after collision. That's after collision. So now, what is the principle of conservation of linear momentum? The sum of momentum before collision is equal to the sum of momentum after collision. So before collision, we have the mass of A and we have the initial speed of A. Okay, before collision, we have the mass of block A or ball A, and we have the initial speed of ball A. So which means their momentum becomes what? Or the momentum of ball A becomes mass of A times the velocity of A. Whereas the momentum of block B becomes mass of B times the velocity of B. This is under what? The initial condition before collision. So let's now sum their reactions and see. Let's now sum the momentums and see. So before collision, we have that momentum is going to be equal to mass of A times the initial speed of A. Now plus mass of B, but now we are going to be indicating the mass of B, okay, plus mass of B times the initial speed of block B. But we are going to be indicating this now with a negative sign. Okay, I will tell you the reason why. So times minus mass of block B times the initial speed of block B. The reason why we're using a negative sign now is because the two balls are moving what? Opposite one another. Remember Newton's third law, action and reaction are equal, but they are opposite in direction. So since these two balls are opposite one another, it means that they are moving with what? Opposite signs. So whereas A is positive, B is going to be what? Negative, because it is moving opposite the motion of A. So that is why the momentum of B is taken as what? Negative. You can also switch and say minus MAUA plus MBUB. You're still going to be very, very much correct, right? You're still going to be very much correct. Okay. So it means that before collision, our momentum is going to now be equal to, if you evaluate this by taking off the brackets, you're now going to have this to be equal to mass of A times initial speed of A minus mass of B times initial speed of B. This becomes momentum before collision. Now after collision, you're going to have, after collision, now one thing is common after collision. The thing that is common is that the two balls will always move in the same direction. So if you take a look at this diagram, even if mass A is lesser than mass B, it means the two objects will have to now move what? Backwards, because one of the objects must move in the direction of the other. They must now move in the same direction. So that is common for what? Momentum after collision. They now move in the same direction. As such, their momentum becomes what? Becomes a sum of their individual momentum. So we have mass of A multiplied now by the final speed of A plus mass of B multiplied by the final speed of B. So you see now that in this case we are adding the two equations together simply because what? After collision, the two objects moves in the same direction. Now the law of conservation of linear momentum is simply saying that the sum of momentum before collision is equal to the sum of momentum after collision. So before collision, we had MA UA minus MB UB. So this is going to be equal to MA VA plus MB VB, and this is the principle of conservation of linear momentum. This is the principle of conservation of linear momentum. Now, we are going to be applying this principle to solving a problem. Alright, so let's consider this question to explain what we've learned concerning Newton's third law of motion and the law of conservation of linear momentum. Now, the question says, a ball P of mass 6 kg moving with a velocity of 35 meters per second collides with another ball Q moving in opposite direction with a velocity of 25 meters per second. If both balls now move in the same direction of P at a velocity of 15 meters per second, calculate the mass of Q. So we have two balls. Let's indicate them here. Let's indicate them with a diagram. We have two balls. Okay, this is P moving with a speed, let's assume this direction, of 35 meters per second. Now we have the mass of this. Now the mass of this ball P is given simply as 6 kg. So you have its mass to be 6 kg. We have another ball Q moving in the opposite direction. Ball Q moving in the opposite direction, and it has a speed of 25 meters per second, but the mass of Q was not specified. So we'll keep that as M. Now, this is a situation before collision. So before collision, what then is our momentum? So this is before collision. Before collision. Alright. So remember, momentum before collision, let's call that P, is going to be equal to what? The sum of the momentum of ball P and that of ball Q. So we simply have, it becomes mass of P times the speed of P, right? And the mass of ball P is 6 kg multiplied by the velocity of ball P is given there as 35 meters per second. Now this plus, now the fact that ball Q is moving in the opposite direction to P, we indicate that with what? A negative sign. Now plus the product of the mass of ball Q and its velocity. Mass of ball Q is unknown, so we call that M times its velocity is given there as 25. So this simply means that total momentum before collision P is going to be, let's obtain 6 times 35. 6 times 35 simply gives us 210. So we simply have 210 minus 25 times mass. So you keep this equation, simply call this equation 1. So this is the momentum before collision. Now the question says, if both bodies now move in the same direction of P with a velocity or at a velocity of 15 meters per second. So that means after collision, the two objects now move in the same direction as direction of P. And remember, we assumed earlier P to be moving towards the right. So this means that after collision, what you have is this. So you have your two balls, ball P, ball P, ball P moving to the right with a speed. Now they are moving now at a common speed of 15 meters per second. So with a speed of 15 meters per seconds. You also have ball Q moving in that same direction, okay, with the same speed of 15 meters per second. This is after collision. Not forgetting their mass remains the same. So the mass of P still remains 6 kg, okay, whereas the mass of Q is unknown. We are still looking for this. Okay, so from what we know, total momentum after collision, momentum after collision P is now going to be equal to, once again, the sum of the two momentums. So we have the mass of P, which is 6, times the new speed, or the final speed of P is now what? 15. Now we are adding because these two masses, or these two balls, are moving in the same direction, not opposite one another. So that is what I said earlier. When it comes to the final momentum, or the momentum after collision, the two objects moves in the same direction. So which means momentum after collision must always be what? Adding to one another. So we have plus the mass of Q unknown multiplied by what? The new speed of Q, which is the final speed, 15. So this simply implies that momentum, or the momentum after collision, becomes what? 6 times 15, and that simply gives us 90. So we have 90 kilogram meter per second plus 15 m. You call this equation 2. From the principle of conservation of linear momentum, we said that momentum before collision is equal to momentum after collision, and before collision our momentum equation is equation 1, and after collision our momentum equation is equation 2. We simply equate the two of them together. So equation 1 gave us 210 minus 25m, okay, so we simply have 210 minus 25m is going to be equal to what? 90 plus 15m. So this becomes our momentum conservation. Okay, so from here let's simply collect like terms, right? So we simply have 210, sending 90 over here becomes minus 90. This is going to be equal to, over here I already have 15m. Now let's send minus 25m over here. It becomes plus 25 mass. Okay, so 210 minus 90 simply gives us 120. So I have 120 to be equal to 15 plus 25 simply gives us 40 mass. Okay, so from here it means we can find the mass of block Q to be equal to 120 divided by 40. So this simply implies that the mass of ball Q becomes 120 divided by 40, and that simply gives us 3 kg. So the mass of block Q is simply 3 kg. Now let's compare the mass of block Q, or ball Q, to that of ball P. So you see that the mass of ball P is 6 kg, whereas mass of ball Q is 3 kg. Okay, so this goes as far as explaining what I said earlier, that regardless of the speed, if the mass of one is higher, when collision takes place and after collision, the two objects will now move in the direction of the ball or the object which has a higher mass, which is why the question says earlier that the two objects moves in the direction of what? Block or ball P, because ball P has a mass of 6 kg, and after solving you find out that ball Q has a mass of 3 kg, which is quite lesser than that of ball P. So the two objects will move in the direction of ball P. Alright, so that's the whole concept of momentum. In the next video, we are going to be solving more examples, and we're going to be diving deep into types of collision, talking about perfectly elastic collision and perfectly inelastic collision. I am sure you want to be a part of that video, so do well to hit the subscribe button right now and turn on your notification bell so you don't miss out on that video when it drops. Also, do well to like this video, comment nicely, and share to your friends. I hope to see you in the next video. Thanks.